Good evening, everyone, and welcome to day 4 of regulatory analytics. So, before we start off, let's do a bit of a recap on what we have covered so far in the first 3 days. We started off by looking at the meaning of regulatory analytics. What are we trying to achieve here? Now, in order to understand regulatory analytics, first you need to understand regulations. Regulations are what? Regulations are a set of rules and laws defined within which businesses have to work. Now, obviously, regulations also apply on individuals, but here we are focusing on businesses. And specifically, we are focusing on corporations. So we are looking at big companies, not necessarily multinational companies, but we are looking at some sort of organizations here. All right. So what is the purpose of regulations? Basically, to have a system of checks and balances, which is very important when it comes to running of any business. As we have seen that there might be a lot of scenarios within which these organizations may not be following the proper rule of law and other such things, right? So in a situation like this, we try to go for having these regulations. Now, despite these regulations, a lot of these organizations are often found complicit in some or the other issue. Now, if they're getting found complicit while having a system of checks and balances, then imagine what happens when they don't have any system. All right. So, next thing. We also looked at the applications of AI and ML within this scope. What does AI and ML do in relation to regulations? All right. So we've gone through a few examples, and today we'll take a look at one example where we are talking about the water quality. All right. So we'll be building on from this example. We'll continue to see how we are monitoring water quality as humans. Today we'll start off by looking at the total drinkable water. Then we'll go towards the water treatment. All these things we'll be focusing on. All right. So this was day 1. In day 2, we understood crisp MLQ methodology. All right. So within crisp MLQ methodology, we have 6 steps. We start off with business understanding. That includes business understanding and data understanding. We move on to data engineering, which includes data pre-processing, feature engineering, and EDM. Then we move on to model building and tuning, where we are building a model and performing hyperparameter tuning on it. The next thing we do is we evaluate the model. We look at the model based on a use case. How useful is the model in relation to a use case? Is it worth the effort we are putting in? The next thing we do is we talk about deployment. And then finally, we look at monitoring and maintenance. And we also understood the ML primer. So ML primer, within which we learned about unsupervised learning. Unsupervised learning is where our y, that is our output, is not known. All right, so we don't know what our output here is. Is it, it can be anything, but we are not aware of it. So in a situation like this, we use unsupervised learning. So today we'll be introducing ourselves to this unsupervised learning, and we'll take a look at something we called as k-means clustering. All right, now k-means clustering is one of the most popular unsupervised learning algorithms that exist in the market because it is very robust and reliable, and it is very useful for larger data sets. So before we do that, let's understand what we mean by clustering. So let's understand clustering first. What is clustering? Clustering is grouping of data, okay, based on features. What sort of features are available to us? We are trying to cluster accordingly. All right. So in k-means in clustering, we are grouping the data based on the various features that are available to us. Okay. So here what we try to do is we try to identify the subgroups that are present within the data. Okay, this within these subgroups, the data points are more homogeneous to each other than they are to data points of other subgroups. Okay, so here we use similarity metrics. Here we try to use the similarity metrics. One of the most common ones is the Euclidean distance. So Euclidean distance formula is quite simple. It is given as x of I minus y of I square plus x of I plus 1, that is x of 2 minus y of 2 square, all the way up until x of n minus y of n square, and we take the square root of it all. Okay, so this is our Euclidean distance matrix. All right, so this is commonly used to group the data together. Now let's see what is the meaning of k-means. Okay, so k-means, as we had discussed, is the best clustering algorithm. There are many different ways in which we can do clustering. There are many different ways. There is also something called hierarchical clustering. We have k-median, we have k-mode. K-means has a few variants. So there are many different clustering methods that are available to us. But k-means is the most useful. It is an iterative algorithm. That means it iterates through the entire data to find the ideal number of clusters. Okay, so it is the best cluster algorithm that is available, and it is an iterative algorithm. All right, so here we try to group the data into smaller subgroups. Whatever data that is available to us, we try to take it and we try to segment it into smaller subgroups. All right. So we do the division is done in such a way that we don't have any overlapping clusters. We don't have any overlapping clusters. That means the clusters are as far away from each other as possible. Obviously, there will be some limitation on how far we can push this clusters. All right. So we try to keep them as far away as possible. Okay. So we take the distance of the data points to the cluster's centroid. Now, how is this centroid value collected? This is the arithmetic mean of all data points within the cluster. All right. However many data points we have, the mean keeps changing. So because of this arithmetic mean, it is known as k-means clustering. All right. And finally, the most important point, we try to reduce the variance between data points in a cluster. So whatever cluster we have taken, we try to reduce the distance, try to reduce the variance between those data points. And this is within a specific cluster. Now let's take an example that we have some data that we are representing like this. All right. So here, dividing them into clusters is quite simple. All of these points belong to one cluster. Okay. Right. So now we have segmented our data into subgroups. The idea is that these subgroups are homogeneous. Homogeneous means that they are similar with each other. All right. Heterogeneous means that there is a difference. So here what we try to do is we try to reduce the distance between the points of the cluster. Whatever the points of the cluster are, we try to reduce the distance between them. The lower that distance is, the better our cluster is. All right. Obviously, they cannot be overlapping, but we try to reduce the distance between the points in the cluster as much as possible. Similarly, we try to keep the clusters as far away from each other as possible. Okay. So here we take something called total within sum of squares. Now what is, let me just erase this. What is total within sum of squares? Now what is the meaning of within sum of squares? Here we are measuring the sum square distance of all data points to each other within a cluster. So we try to reduce this distance. The less this distance is, the better it is. All right. So we try to reduce it, and then we take the sum of all of it, sum of all clusters, and we combine it into total within sum of squares. All right. So this is the basics of k-means clustering. So let's see how it works. In k-means clustering, we have to define the number of clusters from the get-go. That means we have to already define the number of clusters. All right. So this might be a scenario where you are trying to find the total number of clusters before you know the problem. Let's say, for example, we have a data set that focuses on regulation violations. Right. So we have a few here. We have health and safety. We have environmental. We have, economic. So let's say we have three groups here, and we have a data that is talking about the violations committed by different organizations. Now we are trying to group that information based on various factors, but none of these factors actually name the violation. All right. So here we can try to group them based on their similarity, to each other. Now in health and safety violation, we are talking about violation of workplace regulations. What are the various workplace regulations in place? We are talking about working hours regulations. Like if some organization is not working within the set hours, they are making the employees work more than they should be without providing the necessary compensation. Okay, so these are included. Environmental regulation violation could include anything from exceeding the allotted number of from exceeding the allotted amount of pollution allowed, from water pollution, land pollution. There are so many different ways in which we can measure this thing. All right. And then finally, we have economic violations. These include violations of economic law. For example, some organizations are banned from trading, but if you continue trading with them, that would fall under economic violation. Like you are laundering money for somebody, for example. All right. And you could be talking about defrauding people. So there are n number of economic regulations as well. All right. So these are the various kinds of regulations you might be coming across. All right. So it is an optimization algorithm and it tries to minimize the within some squares. That means the variance between each cluster. As we had discussed, less the variance, more homogeneity between the clusters. Okay. So we have to follow some predefined steps here. Step one is select k data points as k centroid clusters. So randomly, k data points are selected as the centroid clusters. Now this k we have to define. All right. So minimum clusters is 1, max is infinity. You can have as many clusters as you want. There is no limitation on that. The number of clusters can keep on increasing to the end of times. Okay, so these can keep increasing to the end of times. Here it should be 2, not 1. My apologies here. The minimum number of clusters should be 1. What? 2. Again, making the same mistakes. Why should it not be 1 and why should it be 2? In one cluster, you're basically including all the data points. What is the point of having clusters then, right? So we will have a minimum of 2 clusters, and then you can keep increasing till infinity. So we have to define this number of clusters before we do anything, and then randomly centroid points are chosen and data points start getting assigned to these centroid points that are chosen as the cluster centroids. And as you know, we are taking the arithmetic mean as the centroid point of all data points. So based on that arithmetic mean, based on these points getting reassigned, the value of the centroid keeps getting updated. Okay, the centroids keep getting updated. All right. So before we do that, we define k data points as k centroids. Then we calculate the distance between all data points to the centroid k clusters. Let's say here we have defined 3 clusters. We take this, and this as the centroid point. We then have some data points randomly spread out throughout the data. All right. So what we do is we calculate the distance from each point to each centroid cluster centroid. All right. And it keeps getting added to that cluster. And then we are basically assigning it to the nearest cluster, whatever value is closest to the centroid. Okay. Then we recalculate the new data points, the new centroids. Okay. And we keep repeating this step until the algorithm stops converging. This convergence happens when data points continue to move between clusters. That means, let's take an example of this one. For one cluster, it is getting assigned here. The second cluster, it is getting assigned here. The third time, it is going back here. The fourth time, it is coming here. So we have to keep doing this until it stops converging. Another way to do that is to put a limit to the maximum number of clusters you can form. For example, here we say 15. So we say that the maximum number of clusters we can form is 15. So only 15 clusters would be formed, and that is where our algorithm would stop. And then it would do comparison for the k clusters, which one is the best. We can also give logical names. For example, we were talking about the environmental regulation violation, the health and safety violations, the economic violations, and so many other violations are there. So when we are talking about it, we are giving it some logical name. So this logical name we can assign to each cluster. This will be helpful when we are trying to visualize our data. All right. Whenever we are trying to visualize our data, this becomes extremely important. Okay. So there are a few important points. We use something called the elbow curve. We have seen that we are calculating the total within sum of squares, right? So we take the total within sum of squares and we put it on y-axis and we put the number of clusters on the x-axis. So we have, let's say, 2, 3, 4, 5, 6, and so on. So here, let's say at 2, we have this value of TWS. At 3, it is this value. At 4, it is this value. At 5, it is this value. At 6, it is this value. So this is roughly what our elbow curve looks like. Now, if we focus on our own elbow, what is elbow? Elbow is the joint on our arm that is helping us move our arms in different directions, right? You can move your arm because of this elbow. If we didn't have this elbow, we would have straight arms. We would all be sitting like this, right? So here we are trying to identify the elbow. And as we can see, the elbow seems to be forming at number of clusters equals to 3. Wherever this is our ideal number of clusters. Okay. So this is what we mean when we are talking about elbow curve. We also use something called the silhouette score. So the silhouette score is something that we will cover at a late cover when we are going through our program, going through our code. Okay. All right. We can also use the domain knowledge and customer requirement. If your customer comes to you and says that, hey, I need 7 clusters, then you form 7 clusters, right? Or if you are familiar with the domain, right? If you are familiar with the industry you're working on, then you would have some idea on how many different groups we have. So based on those different number of groups, we can define the ideal number of clusters. Okay. All right. We can use within sum of squares and between sum of squares. Within sum of squares, we have already covered. Between sum of squares, BSS, is the distance between 2 clusters, or distance between one cluster to all other clusters in the group. Okay. So this we can also use, but we are normally using it. We are normally using within sum of squares because within sum of squares is giving us a better idea on the homogeneous, how homogeneous our clusters are. Okay. All right. This is very useful for larger data sets. If you have a smaller data set, this is good, and you can try out different clustering techniques. But if you have a larger data set, then k-means is probably the best. Then we are not getting a dendrogram here. A dendrogram looks something like this. We are dividing the group data into a smaller part. This is part of hierarchical clustering. So that is something that is not available here because with a larger data set, visualization becomes very difficult. Okay. All right. So uh, let's move over to our code. So let me just open up Anaconda, please. All right. So Anaconda Navigator is open, and we'll go to Jupyter Notebook. All right. So this is our data set. We are looking at the total water resources of each of different nations over a different period of time. All right. So let's talk a little bit about these libraries first. Pandas is used to work with data frames. NumPy is used for numerical calculations. And arrays. Arrays are memory storage units. Seaborn and Matplotlib are used for visualization. Okay. So this is our libraries that we'll start off with. So let's look at our data set. So we'll import the data set, and this is what our data set looks like. So here we are trying to measure the total quantity of fresh water per country. All right. So we are looking at how this fresh water is generated and how much is it generating. Okay. So we are also looking at evaporation and transpiration. We are looking at internal resources, outflow total, this precipitation, total renewable per capita. So we are looking at different kinds of sources for water being generated. All right. So this is our data set. So first we'll perform EDA. So here, most of the columns don't have any missing numbers, but these columns have, we have 324 rows. These columns are basically all empty. Okay, so we will simply drop them. And we also check for duplicate values, if there are any duplicate values present or not. And the answer for that is no. There are no duplicates value present in our dataset. All right. So moving forward, so we will drop those columns and we'll rename our water column into water 1. So we can either make the same change into the same column, or we can leave the original dataset as it is and we can start making sub datasets. So we have a track. So we check the info. What is the info telling us? Info telling us is the range, total number of rows. It is telling us how many non-null items we have. That means how many non-missing items we have. Okay. And then it is telling us the data type, whether it is string, int, float, etc. Okay. So this is the values that we are getting from water1.info. Now similarly, just as a experiment, if I add water.info, here we can see that these columns were basically empty. they did not have any value in them. All right. We can also look at the actual data set to verify the same information. So as you can see, these columns are empty. Okay. So we don't have any values there. All right. So we'll close this. We'll close this as well. And we'll go back to our data set. Okay. The next thing we'll do is water1 dot describe, where we are trying for it to describe the numerical values. So we have three numerical columns in origin. We have EA, power code, and the value. This value column is the total water resource. Okay, so here we can see that we have zero deviation. This means we have zero variance. So we have a zero variance feature. Two of them, as a matter of fact, in our data set. So we'll try to remove these zero variance features. We'll check for the variance as well, because we observe that, and we see here that two of these values have zero variance. All right. So I will remove them, create a new data frame, and then we'll check for outliers. Now, let me just increase the size here. So here we can see that we have a few outliers. Now, normally we would treat these outliers, but here these outliers may represent actual quantity of water. All right, these may represent an actual quantity of water. So we'll keep these as is for now. If required, we can always come back and delete it. Then we check for the number of unique values. Here we see that we have a few more columns that have only one unique value. That means we can remove them. The rest we will keep. Country and COU is the country code, variable, and var. Var is the code for variable. So we will remove these as well. So these are the columns that we are left with. Then using label encoding, we will label encode it. We will create some labels and will assign it to each of these values. Then we'll draw a pair plot to understand the relationship between these features. So here again, we'll try to increase the figure size. All right, I guess it is maximum. So here, let's see. So here we are looking at the histogram for each value. How many times are those values coming? Okay. Then we are also looking at the scatter plot. The scatter plot of, for example, country in relation to the variables. So these are the various variables in relation to the various countries. Similarly, countries in relation to the value of water. So here we can see that we are already seeing some sort of clustering happening. We can already identify a few data points as separate from rest of the group. All right, moving forward. Now we will build a k-means clustering here. So first, we'll import our k-means library from sklearn. We'll create an empty list to store the total within sum of squares, and then we'll define k as a list of range 2, 3, 4 all the way to 11. So we are going from 2 clusters to 11 clusters. All right. So this would be step 1. So we enter. Now we'll fit our values and we'll draw the box plot. So here what we have done, first we'll look at this and then we'll go through our elbow curve. So first we are defining the number of clusters as I. I is going through k. So that means k equals to a list of values, so on. And it is going from 2 to 3 to 4 to 5 to 6, again up until 11. So it is going from 2 clusters to 11 clusters, and it is calculating the total within sum of squares between each of these cluster points. Okay, so it is trying to calculate the total within sum of squares between each of these cluster points. Using these points, we can draw our elbow curve. Here we notice that when we are taking 2 clusters, the value of total within sum of squares is quite high, and then it keeps dropping. But here at cluster equals to 3, we observe our elbow. So this would what we would call as our ideal number of clusters. Now another technique that we can use is defined as silhouette score. Okay, so we'll import the silhouette score. All right, and we'll initialize it. We'll let it run. But what exactly is silhouette score? So let's go through that first. It is a measure of goodness of a cluster, of a clustering problem. How good fit is that clustering problem? Okay, the values range from -1 to 1. Okay, if it is 1, that means the clusters are well differentiated. That means there is a lot of difference between the clusters. 0 means they are indifferent. That means we cannot tell the clusters apart from each other. And 1 means they are assigned in the -1, sorry, in the wrong way. All right. So this is how we measure silhouette score. But how is it working in the inner part? It is given as b minus a divided by max of a and b. What is a? A is the average distance between each point within a cluster. All right. B is the average distance between the clusters. So in A, we are taking total within sum of squares, a concept similar to that in A. In B, we are taking between sum of squares, all right? And we are trying to find out our silhouette coefficient, all right? So this is how we calculate our silhouette coefficient. So using this, we can verify whether taking three clusters is a good idea or not, or should we go with the different clusters. All right, should we try with something else? Should we maybe take something that is more differentiated, right? We are already seeing that our distance between the clusters is reducing massively after between second and third cluster. Maybe we should have gone for 4 or maybe even 5. A small elbow forming here as well. Maybe we should have gone for this instead of this. So that is something that we'll verify now. So here again, we take the k value from 2 all the way to 11. Okay, we fit it on our data set. This is all something that we have done before. We are just taking a variable called clusters and we are creating a label. And then we are trying to find the silhouette average score using the silhouette score function between water final, that is our data set, and the clusters. Which clusters is the best fit cluster for our use case. All right. So this basically acts as an additional confirmation for what we are looking for. Okay. Then we'll clear our data. Now here is our silhouette score. Now as we know, silhouette score is between 1 to -1. 1 is the best, -1 is the worst. So at 2, it is nearly 1, but at 2, the total within sum of squares is high. At cluster 3, it is what? Around 0.97. That means it is very, very good. That means there is a sufficient amount of difference between the clusters, more than sufficient amount of distance between the clusters. So in a situation like this basically confirms that taking number of clusters as 3 is a good idea using the elbow curve plus the silhouette score. Okay, so this is how we find out our ideal number of clusters. All right, so this is done. So now that we have decided that we will go with 3 clusters, we have to redefine our model for 3 clusters. So we'll fit our model for 3 clusters and we'll take a look at the labels. As you can see that most of the data belongs to one cluster. So maybe we made some mistake while we were attempting to do the pre-processing. So we should have probably gone with a different pre-processing technique. All right, then we'll add labels here. We'll look at the cluster and then here we have our clusters assigned to each value on the column. At the end, the cluster column has been added. Okay, so now we have clustered our data. Okay, so this is how clustering works when you are working with the unsupervised data. All right, so with this, we finish today's session. So next week, we will switch over to supervised learning and we'll continue on with supervised learning towards the end. All right. So thank you everyone for joining and enjoy your weekend.